Good afternoon. Myself K. Sheikdavood, Assistant Professor, M. Department of ECE, M. Kumarasamy College of Engineering. My topic is application of Boolean algebra in minimization of Boolean expression. So already we know that what is Boolean expression. The Boolean expression is consisting of variables, constants and operators like product and sum. Here what is the purpose and what is the application of Boolean algebra? In electrical and electronic circuits, Boolean algebra is used to simplify and analyze the logical or digital circuit. Here, the logical or digital circuit will be mainly used in digital computers. It's like a microprocessor. So, where we need to use more logic gates and we want to cross-check like analyzing with the help of this Boolean expression and Boolean algebra. So, to minimize the cost and increase the speed, we need to go for a minimization techniques. So mainly this is suitable or mainly used for the purpose of digital circuits like computers, like digital computers. Here the purpose of this minimization techniques of your Boolean expression is to improve the cost and improve the speed and efficiency. Improving the cost, it's nothing but reducing the cost. So when we design any digital circuits, we need to focus on the cost as well as the performance. So cost wise we want to reduce, and to improve the performance like increasing the speed and efficiency, we can go for this minimization techniques on Boolean expressions. This is the major application of your minimization techniques in Boolean algebra. So it is used to perform logical operations in digital computers. Already digital computers use the logical operations like and, or and not. And is act a product term and or is a sum term and not is the inverting term. Now we can see in terms of digital computer, the logic high, that is 1, will be acts like a true condition because computers can understand only true or false conditions. Here the logic low, that is 0, will be considered as a false, that is low voltage. So these are the some logical operators like and, or, not. This will be called as basic gates. Next, minimization of Boolean expression. The different Boolean rules and theorems are used to simplify the Boolean expressions in this method. Though different rules are like distributive law, associative law, inversion law, like we are having a more number of laws and theorems. Apart from that, we are going for next topic. It's named as standard form of SOP and canonical form of SOP. Standard or canonical both will be meaning the same term. So canonical form of SOP and POS. So first, POS is nothing but product of sum. SOP mean for sum of product. So here it is canonical SOP and canonical POS is different from normal POS and SOP. How now? This canonical SOP is the derivation or expansion of Boolean expression. Normally the canonical forms are not minimal, it will be a very large one. Large, that is more number of terms, and we need to use more number of logical operators. Minimization of Boolean expression is needed to simplify the Boolean expressions and thus reduce the circuitry complexity. So we have used this minimization technique. Now we can reduce the complexity in the designed circuits. It uses less number of gates to produce same output that can be taken by a long canonical expression. If we are having a canonical expression or standard expression of Boolean expression, it consists of more number of variables and more number of operators. But when we are including the or we are going for a minimization techniques, we can reduce the number of variables and number of operators and we can give the same output. So for the purpose only we are going for a minimization technique. So before starting a canonical SOP and canonical POS, we can go for next is what is SOP and what is POS. So Boolean expression can be represented by either in two form. One is named as sum of product form, or else second one will be product of sum form. So this simply named as SOP the product of sum will be denoted as POS. So two examples are given here, that is, one is AB plus AC. So this expression consists of only two variable in a term. In a first term we are having a AB, then we are having an operator, that is OR operator, then we are having a second term only with two variable AC. So here this operator is denoted as sum. This between A and B we are having a product term, so it will be named as sum of product. So first we are summing, which we are summing now, the product terms, that's why named as sum of product. Similarly here between these two terms we are having a dot product, nothing but product term, so it will be named as product of. So what we are going to product now, A and B, that is here it will be having a sum, so it will be named as product of sum. So based on the terms, between the terms what's the operator we are having, that will be comes first. So here it will be a sum, here it will be having a product, so sum of product, here it will be a product of sum. So in the above examples both are in SOP and POS respectively, but they are not standard or canonical SOP or standard or canonical POS, because we can see next slide. So this is the normal POS and SOP. So first if you are taking a SOP now, that is nothing but sum of product, and also named as DNF. Instead of SOP we may also named as DNF, nothing but distinctive normal form. It is a summation of product terms. Simply we can say summation of product term. For example, we are considering a function y equal to AB plus A B bar C plus A B bar C bar. So between the each term we are having a summation. So here between the variable we are having a dot product. So it will be named as summation of these product terms. So that's why it's named as SOP. Just opposite to this is your product of sum, that is product of sum, or else CNF, conjunctive normal form. SOP na disjunctive normal form, POS na conjunctive. So here it is the just opposite to here. Here we are having a summation of product term, here it will be a product of sum term. So product of the sum term na, between each term we are having a product term, product, and between the variables we are having a sum operator. So that's why it's named as product of sum. So this is the normal SOP and POS. It will be different from your canonical form. Now we can go for canonical form of Boolean expression. In standard SOP and POS, each term of Boolean expression must contain all the literals. So literals nothing but our variable with and without bar, that is with or without complements, that has been used in Boolean expression. If above condition is satisfied by the Boolean expression, that expression will be named as canonical form of Boolean expression. Or again I am saying that here standard form of SOP or POS must contain all the literals, that is nothing but all the variables should be present in the expression. If it is so, it will be named as standard or canonical form of SOP. So here you can see some example in the Boolean expression AB plus AC. So only totally the function consists of 3 literals, but each term will be having only 2 literals. So we can see the literal C is missing from the first term. So this is the product term. In the product term first we are missing C, and in second term we are missing the literal B, that is we are having only AC, we are missing out B. So if so, this expression is not a canonical form of Boolean expression. As already I mentioned, all the literals should be present in the each term of your canonical form. So that's why AB plus AC is not a canonical SOP. This will be named as simply SOP, sum of product. So you can see the difference between canonical form of SOP and canonical form of POS. So here the canonical form also named as standard form. So that's why the standard form of SOP will be denoted as SSOP. The standard form of POS is denoted as SPOS. So nothing but it is a standard or canonical form of SOP. This is standard or canonical form of POS. So that what's a condition, as we already said, each product term contains all the variables of the function. So variable nothing but our literal. Here all the sum terms contain all the variables, nothing but your all the literals of the function. So example given for this, standard SOP, here given for standard POS. So standard SOP example is function of A, B, C. So in the function itself they mentioned that it has 3 literals A, B, C. But in the expression, see that we are having A, B, C. All the literals are present in the first term. Second, A, B bar, C. So all the literals will be present. It may be a complement or uncomplement. No issues, but it has the literal here. Here we are having a B, C bar. So here also all the literals will be present. So if this will be considered as a standard SOP, it is not SOP, standard sum of product. It will be a standard sum of product. Just same as like the SSOP, the SPOS is each sum term contains all the literals or variable of the function. Example here also given as function of A, B, C. 3 literals have given. So the term is A plus B plus C bar into A bar plus B plus C. So totally 2 terms. All the 2 terms will be consist of all the literals. So it will be named as standard form of product of sum or canonical product of sum form. So these are the 2 major difference between canonical form as well as your normal SOP. So we can see the steps to convert standard SOP to standard SOP. The first one is find the missing literal in each product term. If it is a SOP na, we want to check with the product term if any literal will be missed. If so, next we want to go for and each product term having missing literal with the term formed by ORing the literal and its complement. Suppose if any literal is missing na, we want to OR the missing literal with its complement. For example, in this term A, B, C is missing na, we want to and na just multiply with its complement, missing literal and complement we want to OR. So we want to write C plus C bar. So the first term will be multiply with C plus C bar. Already we knows that as per the Boolean laws and theorems, A plus A bar is 1. So multiplication of 1 with any variable will get us any variable. So next, after this process, we want to expand the terms by applying the distributive law. So distributive law already we have seen in our Boolean algebra. So then we want to apply the distributive law. After applying the distributive law expansion, we want to go for reorder the literals in the product term. So again we want to reorder. So after reordering, again we want to reduce the expression by omitting the repeated terms. Suppose if you are having AB plus AB na, we may write only one AB. Since already in a property, it will be mentioned as A plus A equal to A. This is the steps to convert SOP to standard SOP. Next we can go for steps to convert POS to standard POS. Right? So here find the missing literal in each sum term if any. So here we are used product term, here want to use sum term. And or each product term having missing literal with term formed by ANDing. So here we have done the and we are doing the OR process. Here it will be ORing the AND process. After that, same expand the terms by applying the distributive law and reorder the literals in the product term. The same, then reduce the expression by omitting the repeated term. So as per this conversion steps, we want to first check the missing literal. Then if it is SOP, we want to go for product term and we want to product with ORing function, missing literal C plus C bar, for example. In the same opposite to this SOP, POS will be just ORing the AND literals. For example, if your C is missing na, you want to OR, just you want to add with C into C bar, so that the value will be remains same, it won't be changed. This is the steps to convert normal POS and SOP into standard form. We will go for an example, canonical form of Boolean expression, that is convert, as we seen the previous example, AB plus AC in canonical SOP. We want to convert this normal SOP into canonical SOP. The solution is first write the terms expression AB plus AC. Then we want to check the first step, which literal is missing in the term. If as per our concern, in a first term the literal C is missing, in second term the literal B is missing. So as per our step, first we have finded the missing literals. Next will be, it is a SOP that you want to go for a product, that is ANDing the missing literals and its complement literal. So here complement of C is C bar. So just we are producting the C missing literal with plus R in form and C dash nothing but its complement form. So C plus C bar is nothing but 1. 1 into AB will be remains will get as same AB. Likewise here missing literal is B. You want to R the missing literal with its complement B plus B bar. The value of this B plus B bar will be 1. So you will get as such. Now we want to apply the distributive law. Already we know that distributive law is nothing but A into B plus C equal to AB plus AC. Just a simple like a multiplication. When you are applying this, the A, B and C, we get a first term. Then A, B, C bar, it's a second term. Again you are having a plus term. Then A, C, B, you can write as A, B, C. Next A, B bar, C. So you got the simplification after the distribution law. So after that you want to remove the repeated literals, that is repeated term. So see that in this step we are having A, B, C. Again we are having a B, C. So two terms will be repeating. So as per our the property A plus A equal to A. So we can write only one time. So we are getting as A, B, C bar plus A bar, A, B bar, C. So we can leave the common term. So this is the conversion of SOP into canonical SOP. So just look on it. Here we are having a B plus AC. Here we are having a B, C bar plus A, B bar, C. So for example, if we need here 2 AND gate and 1 OR gate in the sense to cross check the expression, here we need 3 AND gates and 2 OR gates to cross check this expression. So from converting from SOP to canonical SOP, here the number of gates and time and cost will be increases in canonical SOP. Again, we can go for next step, that is converting the POS into canonical POS. So as already we said that POS is nothing but product of sum. So in this product of sum, we are having a plus B, another will be A plus C. So now first step as we given in the conversion, the first step is finding the missing literal. In the solution, first step will be the A plus B. Here the missing literal is C. In second term, the missing literal is B. So after identifying the missing literals, we want to go for a either it should be a AND or it should be a OR function. So as per our steps, so OR the each product term having the missing value. So you want to go for AND function, that is C and C bar. You want to AND the OR. So here there we have done first multiplication of sum term. Here we are going to do the summation of product term, that is you want to first AND OR, then you want to AND. So there you have written as C plus C bar. Here you want to write as C dot C bar. In POS we have just multiplied the term with the expression. Here you want to add. So if you after here missing literal is C, so C dot C bar. Here missing literal is B plus B dot B bar. Now we want to apply the distributive law. So already we know the distributive law in the Boolean algebra. So here just multiply A plus B again plus C. So you can write as A plus B plus C. Then product term, we are having a product term here, same product term. Next will be A plus B plus C bar, second term. Then again dot product. Next A plus B plus C. Again dot product A plus B bar plus C. So we are getting a after applying this distributive law, you want to check whether any term will be repeating. Yes, it is here repeating as A plus B plus C. Again we are getting A plus B plus C. So as per our law, A plus A equal to A. So we can repeating term will be duplicate will be removed off. So remaining is A plus B plus C dot A plus B plus C bar dot A plus B bar plus C. So this is the canonical form of POS. Just compare. Here we have one OR gate, here one OR gate, here one AND gate we required. So actually 2 OR gate and 1 AND gate is required. But in this area we need to use step 3 input OR gate, 1, 2, 3, 3 input OR gate, and we want to use 2 AND gates or else 3 input 1 AND gate. So the number of gates and cost will be increases, but it will be giving the same output and same efficiency, but the cost base will be increased. So on space and memory also get increased. So to avoid that, we can prefer the normal form of SOP or POS. So when we are converting from POS to canonical POS, we want to follow the same steps. So these are all the two example of canonical or standard form of Boolean expression. So once again I will repeat the same. Normal SOP will be nothing but product of sum, and POS will be product of sum. There is no finding of missing literals. This is the minimized expression for both POS and SOP. But if you want to convert into SOP to standard or canonical SOP, or POS to standard or canonical POS, we want to follow the steps. So here what happens in the when it will be condition will be satisfied, it will be what condition now? All the literals will be present in each term. So if it is satisfied now, it will be considered as canonical form. So example is given here. Next you can go for canonical form. Two types of canonical form, canonical SOP and canonical POS. So here is the example given. The function ABC, the variables are a comma b comma c. All the variables or literals will be present in each term. So it will be considered as canonical SOP or standard SOP or SSOP. Here it will be canonical form of POS or standard form of POS or SPOS. So this is the difference between normal and canonical form. Normal SOP and POS and canonical form of POS and SOP. So these are the example problems. One is converting SOP into canonical form. Another will be converting POS into canonical POS. Thank you.